All right, welcome. In this third and final segment of graphing sine and cosine functions, we are going to look at an example of graphing a cosine function. So again, first thing we want to do is find the period, amplitude, and midline of the function. So our period, remember, is calculated by taking the period of the parent function. Cosine and sine both have a period of 2 pi, and dividing it by the absolute value of 1 over b. So what we have to understand here from this structure of x over 3, that this is the same thing as 1/3 x. So this 1/3, that is by definition our 1 over b value. So we are taking our 2 pi and we are dividing it by the absolute value of that, which is 1/3. Well, that's the same thing as 2 pi times 3, which tells us that the period is 6 pi. So that means that in 6 pi radians, we are going to see one full complete wave for the cosine function. The amplitude, remember, is by definition the absolute value of our a parameter. And our a parameter this time is -2. So we're looking at the absolute value of -2, which would be +2. And what this means is that that is basically half the distance between the relative minimums and maximums for the cosine function, and the distance from the midline to a maximum or a minimum. And the midline is y equals k, remember, and in this function there's no addition or subtraction after the cosine of x over 3, so that means y equals 0 is our midline. That's our k value then of 0, and y equals 0 is the equation of the x-axis. So our x-axis is our midline. And the zeros always occur on the midline. So that helps us know that all of our zeros are going to be, the zeros, the transformed zeros of the function are going to be on the midline. And so they're going to stay on the x-axis this time because we're not shifting up or down. No vertical shifts yet. All right, so now what I need to do is figure out what scale do I want to use here, or what scale might be helpful to me. So I'm going to take my period of 6 pi radians and divide it by 4. And that gives me 3 pi over 2 radians as a possible scale. Now you can change this if you can have enough squares to make it work. But we're going from -6 pi to +6 pi. So I don't know that we want to mess around with that too much. So I am looking at kind of dividing this in half if I have to go from all the way from -6 pi to +6 pi. And on my y-axis, because I have an amplitude of 2, I think that I will use a half unit scale. So I'll make this 1 and this 2. And this will be -1 and -2. And then if I use a 3 pi over 2 scale, then what I'm looking at is kind of doing, this would be 1.5, and this would be 3, and then 4.5, and then 6. If you want to, you can use a scale of pi and do 1, 2, 3, 4, 5, 6 pi, but then you have to keep track of your halves when you're doing things like that. So I'll show you what that would look like if you would rather use a scale of pi. We can give that a try. So let's try a scale of pi. It's a little easier to work with for the parent functions. So this would be pi and 2 pi and 3 pi, 4 pi, 5 pi, and 6 pi. And in the negative direction, this would be -pi, -2 pi, -3, -4 pi, -5, and -6 pi. So we're going to look, and because our period is 6 pi, we're going to have 2 full complete waves in this interval of -6 pi to +6 pi. All right, so now, as we talked about, one of the strategies you might like to use is to first start off by graphing those 5 key points that include the zeros and the relative maximums and minimums of the parent function. So cosine of 0 is 1, so it starts here in the parent function. And then at pi over 2, which would be this halfway line, it's at 0. And then at pi, cosine is -1. And then at 3 pi over 2, it's back to 0. And at 2 pi, it's back to 1. So these are the 5 points of the parent function that we're going to transform. So let's talk about our transformations now. So we go back over here to our parameters. So this 1 over b of 1/3, remember we want the reciprocal of that. So that tells us our b value is 3. And so that tells us that we have a horizontal stretch by a factor of 3. And then our a value being negative, its absolute value is 2, so that tells us we have a vertical stretch by a factor of 2. And the fact that it is negative tells us we also have a reflection across the x-axis. All right, so you can do your vertical stretch and reflection first and then do your horizontal stretch, or you can do your horizontal stretch first and then do the vertical step. It's your choice. Either way will work. So for example, let's take this point right here of 0, 1. So if I do the vertical stretch first, it would stretch to 2 because we're stretching by a factor of 2. Then it would reflect down to -2. Now, because it's on the y-axis, it would not be affected by a horizontal stretch because its distance to the y-axis horizontally is 0. So it's going to stay there. The next point I'm going to transform is this one. So this one is, because it's on the x-axis, it's not going to be affected by the vertical stretch or the horizontal stretch. Or sorry, the vertical stretch or the reflection across the x-axis. It is going to be affected by the horizontal stretch. So its horizontal distance of this half unit here is going to be multiplied by 3. So that would be 1.5. So this would be 1, 2, 3. So it's going to end up right there, actually. So we're going to have to remember that was one of our original parent function points right there. So now we're looking at is this one. So this vertical distance of 1 unit below gets stretched to 2 units below. And then it gets reflected up here to 2 units above. And then this horizontal distance of 1 square gets tripled to 3 squares. So that point is now here. Then we had this point, remember, which we kind of colored over. So again, this one, because it's on the x-axis, is not going to be affected by the vertical stretch or the reflection. But its horizontal distance of 1.5 units is going to be tripled. And so that 1.5 times 3 is going to give us 4.5. So 1.5, so we're going distance of 4.5. So 1, 2, 3, 4.5, and it would be right there. And then our final point here, so this vertical distance of 1 unit gets stretched by a factor of 2 to 2, and then reflected down here to -2. And this horizontal distance of 2 units gets tripled to a distance of 3 units, or sorry, 6. 2 times 3 would be 6. So we have 1, 2, 3, 4, 5, 6, and it ends up right there. So there's the first wave of our transformed cosine. You have to remember these are minimums. So what we're seeing here is the bottom of our valleys or troughs. And then it's coming up to its maximum, hitting that 0, heading down towards this minimum. So what's going to happen is the same thing on this other side. So 1.5 units reflected will be right there. And then this point, 3 units was reflected over there. And this point right here, which is 4.5 units, gets reflected there. And this one, which is 6 units this way, is 6 units that way there. And that will allow us to complete the graph of the cosine function. The wave's not exactly very smooth up here. That will give us basic graph of this cosine function over this particular interval. All right, and that is the last example. There are a couple of practice problems, which if you'd like to, you can pause here and give this one a try. Test yourself. Here is what the period, amplitude, midline, and the graph is in blue, what it should look. The black is the parent function that was transformed, that first cycle of the parent function. And here is a second practice problem, a cosine function. And then here is what you should have for period, amplitude, and midline. And this is the graph of g of x, and this is the parent function's first cycle that was transformed. And your closure, what I'd like you to be able to explain, is what it means to say a function is periodic. So, if you said something like a function is described as periodic means that its output values of y repeat over a specific interval, which is called the period of the function, then you've got the right idea. So, for example, our sine and cosine function values repeat every 2 pi radians. That's the parent functions are periodic over an interval or period of 2 pi radians. All right, so that concludes the full lesson, and you should be able to now look at each of the different problems on the assignment.